cloud chambers are an excellent tool that enable us to visualize some of the effects of not only nuclear radiation, but also cosmic rays. Now, the first stage in constructing our cloud chamber out of these materials is to pre-cool our baking trays with frozen carbon dioxide, dry ice. Making sure I have my thermal gloves. The amount of dry ice I need is relatively small, but enough to completely cover this layer of the baking tray. Now, it's important to make sure that it's spread out. You can sometimes hear some rather odd sound effects as the metal starts contracting. Now, our second baking tray has got a laminated piece of black card on it. This is to improve the contrast effect once we start using our cloud chamber. And so carefully, I place the second tray onto the first tray and I leave it to one side, allowing it to pre-cool. Our next stage is to prepare the main body of the cloud chamber. This is a plastic aquarium. We have a felt strip here, which I'm now going to soak with propan-2-ol. Our next stage is to line the bottom of the tank with our sealing material to make sure that when I place it in its final position in the cloud chamber, it's going to be almost airtight. Having prepared our tank, I'm now going to take my tray off, having pre-cooled it. I'm going to put some more dry ice into the tray. We spread the dry ice out. Now, before we place our second tray back in position onto the cooling tray, we need to put our radioactive sources, our alpha or beta emitters, in the correct position. In this case, we're using thoriated rods, one of which we've covered in a layer of paper. And now I'm going to place my tank in position onto the first tray, pushing it down into position so that I'm sealing it on. We place the cloud chamber now onto its cooling tray, once again push down to seal into position, switch on our illumination source, and we wait. Why are we seeing these beautiful contrail events inside the cloud chamber? Well, both of these rods are emitting, through radioactive decay, alpha and beta particles. Alpha particles are helium nuclei, whilst beta particles are high-energy electrons ejected from the nucleus of an atom. Both rods are producing alpha and beta radiation. Alpha radiation is composed of much more massive but slower moving particles than beta radiation. And this means that in air, the range of alpha particles is only a few centimetres. They're easily absorbed by a layer of paper. Beta particles, however, have got higher energies. They'll penetrate for much longer distances in air, and so when we compare the two rods, the one that's not covered by paper is emitting alpha and beta particles, and we're seeing both types of trails. However, for the rod that's covered in paper, most of the alpha particles being emitted by that rod are getting absorbed by the paper. And so the trails that we're seeing emerging from that rod are much longer in nature. They're marking the trails of beta particles being emitted. As they move through the gas inside the cloud chamber, they're knocking electrons off the gas molecules. They're creating ionisation trails along their path. And it's along these that the propan-2-ol vapour, which is saturated, can start condensing, forming a contrail marking the paths of the alpha and beta particles being emitted by the rods. Occasionally, we see a contrail that has no connection with either of the rods and seems to come from any direction. These are evidence of cosmic ray events. High energy particles from deep space impact the Earth's upper atmosphere and produce secondary radiation called muons. And what we're seeing with these completely unconnected contrails are evidence of muons interacting with the gases inside our cloud chamber. In this demonstration, we've seen lots of radiation events associated with the thoriated rods, but relatively few of the cosmic ray events. That's because down here on the Earth's surface, we're protected by the Earth's atmosphere, but also by the magnetic field. And so for any spacecraft orbiting more than a few hundred kilometers above the Earth, it doesn't enjoy the full protection of Earth's field, posing continuing challenges for space scientists and engineers.